Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Ladies and gentlemen, may I have your attention? Kindly mute your mic as our webinar is about to begin. Alhamdulillah, our honorable guest, Professor IR Dr. Muhammad Azmi Ayub, Dean of Academic and International College of Engineering, UiTM, Professor T.S. Dr. Samia Kasolang, Rector of UiTM Penang, our honorable keynote speakers for the first UiTM Universitas Pertamina webinar series 2021, Prof. Wahyu Kuntjoro from School of Mechanical Engineering UiTM, and Dr. Judha Purbolaksono from the Department of Mechanical Engineering Universitas Pertamina Indonesia. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon. Distinguished guests, ladies and gentlemen, welcome to UiTM Universitas Pertamina webinar series. Before we begin, let us start with Ummul Kitab Al-Fatihah. Amin, amin, ya rabbal alamin. May Allah shower us a barakah for this webinar series. First of all, I would like to invite our honorable guest, Professor Engineer Dr. Muhammad Azmi Ayub, for the opening remarks for this event.
Thank you, Chairman. Dr. Hussain, can you hear me?
Yeah, very clear.
Yeah, okay. Assalamualaikum warahmatullahi taala wabarakatuh. And selamat petang, good afternoon. Yeah. Yang berbahagia Prof. Salmia, Rector UiTM Penang. She is here, and Yang berusaha Head of Industrial Linkage, College of Engineering, also the Moderator, Associate Professor Dr. Muhammad Hussain Ismail, also the Chairman of this today event, distinguished and knowledgeable speaker. I think there are two speakers today. The first one is Professor Dr. Wahyu Kuntjoro, and the second one is Dr. Judha Purbolaksono. And ladies and gentlemen, all the staff of UiTM, first and foremost, I would like to congratulate the College of Engineering UiTM Malaysia and Department of Mechanical Engineering Universitas Pertamina Indonesia for initiating this joint seminar, this joint webinar. It gives me a great pleasure to welcome all the participants, to the staff of College of Engineering, in particular to this webinar series in year 2021. Perhaps this is the first series between College of Engineering UiTM and Department of Mechanical Engineering University Pertamina. Today webinar set a significant milestone for closer research collaboration between UiTM and University Pertamina. I'm really inspired by the theme chosen for this 2021 webinar series on fostering Internet of Things in future research, in line with university and nation, especially Malaysia, nation aspiration in the direction toward the application of Industrial Revolution 4.0. I hope that this webinar event will promote international academic and development cooperation and collaboration in relation to IR 4.0, SDG, renewable energy technology, organization of symposia, conferences, short courses, and meetings. And certainly, network and capacity building, very via collaboration and internalization of university activity, staff and student mobility, joint programs, innovation, and technology advancements have always been a top agenda of UiTM in particular. I think it is worldwide. Now we are talking about collaboration at international levels. Less competition, more collaboration. It is therefore our vision to develop an international innovation and technology hub that will provide solution in IR 4.0, SDG, renewable energy sector, and commercializations of research results. To set up our collaboration in innovation and technology, both university, I hope UiTM and Universitas Pertamina will actively engage in supervision of both at the undergraduate and postgraduate level, joint supervision of students. The main expected outcome of joint supervision is strengthening cooperation through high impact research outcome and high quality journal publication. I hope if Prof. Wahyu and Prof. Judha can help in strengthening collaboration between UiTM and Universitas Pertamina, I think it will be very helpful. Strengthening national research capacity is one of the key agenda of the government of Malaysia. International Cooperation Fund, so Malaysia have a one fund called ICF, International Cooperation Fund, is a grant provided by the Malaysian government for international joint R&D project between researchers from Malaysia and other universities abroad. I hope we can make full use of this ICF grant. The aim of the fund is to provide platform for investment in expanding and enhancing research capacity and increasing collaborative R&D partnership for competitive R&D projects. They are innovative, given high impact, and subsequently contribute to the advancement of knowledge and technology development leading to commercialization. This provides an opportunity for both UiTM and Universitas Pertamina to prepare a research grant application to secure a grant through ICF. The College of Engineering, UiTM, Malaysia, is committed to excellence in the field of education, research, and publication. Moving forward, College of Engineering is looking forward to strengthening academic excellence via staff mobility and student mobility between these two well-known universities. If we can realize this, I think that's not difficult to realize this staff and student mobility. I think that should be very good. On that note, I wish this event a success and hopefully could inspire and benefit the whole university community. I would like to take this opportunity to offer my sincere appreciation to members of the organizing committee for working toward the success of this event. I would like also to thank again Associate Professor Dr. Muhammad Hussain Ismail and all the collaborators for their effort which made this webinar even possible. Thank you very much. Thank you, Dr. Hussain. I pass back to you.
Thank you very much, Prof, for the welcoming remarks. Actually, this is a collaboration work between College of Engineering from Penang campus, which is led by Associate Professor Dr. Koi from Penang. Okay, thanks.
But also, I would like to excuse myself. I have another meeting, so
okay.
Leave this meeting. Thank you very much.
All right, thank you, Prof, for your time. Right, ladies and gentlemen, our first keynote speaker is Professor Wahyu Kuntjoro from School of Mechanical Engineering, UiTM, and his presentation title is Finite Element Method Analysis of 3D Printed Structure. So before the presentation begins, allow me to introduce our first keynote speaker. Prof. Wahyu Kuntjoro is a professor of design and lightweight structure at the Faculty of Mechanical Engineering, University Technology Mara, Malaysia. He finished his first degree in mechanical engineering from ITB Bandung, Indonesia. Subsequently, he worked with ITB and also involved with Indonesian aircraft industry in the field of airframe design and analysis. His master and PhD degrees were obtained from the College of Aeronautics, Cranfield, England. Dr. Kuntjoro also spent a time doing research on structural optimization at Delft University of Technology, the Netherlands. Recently, he was also involved in welding simulation, a research conducted in collaboration with Chemnitz Technical University, Germany. Other than teaching, supervising, and conducting research, Dr. Kuntjoro is actively providing technical consultancies and trainings, mainly to the Royal Malaysian Air Force in the field of fatigue monitoring and airframe integrity. Without further ado, I would like to welcome Prof. Wahyu to deliver his presentation. All right, Prof. Wahyu, the screen is yours.
Okay, thank you very much, Dr. Hussain. So, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everybody. So, firstly, I would like to thank you, Dr. Hussain, for a very kind introduction. And also to Prof. Azmi just now for opening this program. And I heard probably also Prof. Samia, our UiTM Pulau Pinang's rector. So thank you very much. So, okay, so I'm going to open my presentation. All right, so let's start. So what I would like to share this afternoon is what we need to consider when we are doing analysis, simulation to 3D printed structures. Okay, by the way, before I go further, Dr. Hussain, can you hear my voice? Is it okay?
Yeah, clear, very clear.
All right, thank you. So this presentation is prepared by me and my colleagues, Associate Prof. Dr. Rizal, Effendi Muhammad Nasir, Madam Atika, and also Mr. Abdul Malik Hussain, Abdul Jalil. So we are from Flight Technology and Test Center, which is one of the center under College of Engineering, UiTM. FTTC, the head of FTTC is Associate Prof. Dr. Rizal Effendi. Okay. All right. So that is the title of the presentation. All right. So basically, this is what we are going to discuss, or what I'm going to share this afternoon. Well, before we go further, we can see over here some let's say printed products of what we can do when we are using 3D printing. So quite amazing, because many of these are actually very complicated in shape. And that is also part of the reason why we go to 3D printing for certain categories of airplanes that we design, because it can produce complicated shape with a certain level of structural integrity. Okay, so we are going to start with the background, the reason why we do 3D printing for our design and products, and it's not really product and the prototype that we are building. And we are going to look at the parameters involved in 3D printing, because these process parameters will going to affect the material behavior. And next to that is we are going to share what kind of simulations that we do, and in this case, of course, finite element simulation. And I am going to close the presentation by looking at what we need to consider when we are doing modeling and analysis of 3D printed component. Okay, so our background is aerospace engineering. So FTTC is doing aeronautical aerospace engineering. That means that mostly of what we do is airplane or drone or multi rotor. And in this case, yeah, we are going to focus more on the fixed wing, because that's what we mainly use this 3D printing for. So if we look at this picture on the right here, that was around 10 years ago when we built an airplane, a 5-meter wingspan. And the unique thing is that this airplane was powered by a fuel cell, which is unique. And the problem is, at that time, at least, the power to weight ratio of this so-called fuel cell was very poor. So meaning now that we don't have much power and it is heavy, the fuel cell is heavy. That means we need to generate enough lift or enough vertical force upward so that the airplane can fly. But of course, the airplane has to be so lightweight. And so for this 5-meter wingspan, at that time, we built this airplane, the wing and the tail boom made by balsa wood. So you can imagine 5-meter wingspan using balsa wood. Yeah, that's a really fragile airplane which couldn't absorb a lot of punishment, if I may say so. And when we are doing flight testing, incident will happen. So because of that, then we have problems with this airplane. It can fly, definitely, but now that shows our first challenge when we are trying to build an airplane for certain specification, and our problem is more on how are we going to build this airplane and what material. So that is the story for that airplane on the right. Okay, so what about the picture on the left? If you look at that picture, that if for anybody here who are familiar with war machines, so this airplane looks like B-2 bomber, which is kind of flying wing airplane, blended wing body. So that's what we did. This probably beginning about 15 years ago, okay? And again, the challenge here is how are we going to produce this kind of airplane with complicated shape, and the shape, the accuracy of the shape is so important because basically this is unstable airplane. So how are you going to build it? What about the material? So at that time we were really stumbled with this kind of problem. Okay. So yeah, again, how are we going? Again, the question is how are we going to build this airplane? What material? So for comparison, when we design and build small airplane like this, small meaning that the wingspan is less than 1.5 meters. So I will say this probably coming under category of, well, micro probably, or small mini airplane, small mini UAV. Then it is simple. This is made of balsa very conventional airplane, easy to design, easy to build, easy to calculate. So just for comparison, balsa is okay for this kind of airplane. Okay, so now this is another story. This is, I think, around 8 years ago, 9 years ago, 8 years ago. Everybody in Malaysia definitely is going to be familiar with PRGS. So this is making use PRGS grant. We built the prototype of a blended wing body airplane. Okay, tailless without tail, and with canard. So we want to manipulate the flight dynamic and control by using canard. So that was the intention at that time. Mind you, this is 8 years ago. So we built this airplane, and the problem again is, how are we going to build it? This airplane is about 2.5 meter wingspan. So the length or the size of this airplane from wingtip on the left to wingtip on the right is about 2.5 meter. We're going to do balsa. Why we do not want to use balsa? Because this is prototype. And it will do a lot of punishment. Definitely, it would fall down, incident, and indeed that happened. So meaning we need to have a frame that is robust, okay, and can take punishment. So balsa couldn't do that. So at that time, the only thing that we could think of at that time was we built this using composite material. So this airplane is made of carbon fiber, okay, and it was built using aeronautical standard with autoclave, with vacuum bag, that kind of thing. So yeah, indeed, this is a very, very good airplane, airframe wise, and indeed it could absorb a lot of punishment. What's the problem? The problem is this is expensive. The cost of the airframe at that time is about 30 to 40,000 ringgit. The cost of the airframe manufacturing only. So that's expensive. So with that amount of money, we got two sets of airframe. So 30, 40,000 ringgit at that time, mind you. So it is more than, in rupiah, is more than 100 million rupiah. 100 juta rupiah, which is quite impressive, right? In terms of price. Okay, so again, we have having the challenge. How are we going to build the prototype to our design, which is going to be okay, but not so expensive? By the way, we did a lot of manipulation to our blended wing body. Probably it's not so clear to you just by looking at this picture, but only the body, which is body and the wing, which is made of composite. And when we add additional components, like such as the horizontal tail or the tail boom, okay, horizontal tail or the tail boom. So tail boom is this long beam, okay, that's tail boom. This is short tail boom. It is made of balsa and combination with a carbon rod. So yeah, this is a kind of a mixture of various kind of manufacturing process. It was flying a long time ago. Okay, so from here we could see that we were evolving in terms of material that we can use for micro or small mini UAV. meaning that it is going to be below 1 meter, 1.2 meter, 1.5 meter, probably not more than that, then balsa is okay because relatively it is going to be robust for that size, okay? But when we go beyond that, like 2.5 meter, 3 meter, or beyond, balsa is not going to be effective anymore. So that is also part of the reason why we make use carbon fiber reinforced plastic. So we start with wood, balsa, and then we use carbon fiber, which is expensive, as I mentioned before. And by the way, it is not easy to get carbon fiber prepreg, which is up to the standard for this purpose. It is not easy. So again, the challenge is expensive and we need strength and stiffness. Also, manufacturing cost is expensive. So again, it's always going to be the balance between cost and strength. So that's the reason why, beginning from 3 years ago, we begin to look at 3D printing. Okay, so the material that we are working with in our 3D printing is PLA, polylactic acid, not because of what, but because this is easy to get. It is easy to get, relatively cheap, and yeah, not too bad, basically. So what you see here is, I think this picture is about 2 years ago, a few small UAV that we built using 3D printing. Okay, so by the way, this gentleman there, which is standing, that is the head of FTTC, by the way, Dr. Rizal Effendi. He's holding an airplane that is made of 3D printing, and all these 3D airplanes, all those airplanes that you see there is made of 3D printing. And we like it because it can produce complicated shape, which we need, especially when we are dealing with an airplane such as this blended wing body airplane. Okay, so those are the backgrounds. So now let's look at the 3D printer itself. So this is just for a simple explanation on the 3D printing, the detail of it. You can always go to any website, even you can go to YouTube. A lot of the information of those in YouTube, basically. On the right here, by the way, this 3D printer here on the right, and here at the bottom here on the left is our 3D printer. But mainly we are using this 3D printer on the right. So it can do 3-dimensional printing because it can do y-axis, x-axis, and z-axis. So that is the reason that it can do 3D printing. And there are a few things that we need to consider when we are doing the printing. And these parameters will affect the properties of our component. So the printing process that we need to look at is nozzle. So there will be a nozzle here where it is going to eject the hot filament outside, hot material out. It's kind of extrusion, okay, extruding. And there will be few size of nozzle. Also, part of the parameters is the temperature, the printing temperature. And of course, there is going to be consideration on the printing direction, the way we print the product, the direction of printing, the orientation of printing. And of course, going to be important is the filament material itself, but we are not going to talk about it because we are only using one material, which is PLA. And of course, another thing that is important in 3D printing is infill. Okay, all right. One thing that we learn from what we have been doing so far is that normally when we design something, we design a structure, then we need to understand the mechanical properties. Now, unique with 3D printing, when we want to design a product, then you want to manufacture the product, we need to make use as the mechanical properties of the material must be based on the way we print the product. So the mechanical properties that we are going to use must be based on the similar printing process that we do. And then that means we need to produce test specimen which is built based on certain process. And then we are going to, let's say, tensile testing, and the outcome of the tensile testing is going to be used for our product. So meaning that the tensile test specimen must be printed in the same way as we want to print our product, because otherwise then it is not going to be valid. We cannot just simply go to website or look at a journal or articles looking at the mechanical properties of the printed component. No, because the range is too big and it's not going to be the same. So the need to do material testing to the in-house 3D printed material. Okay, so this here is what we mentioned just now as infill. So if it is 100% solid, then that's what you have over there. But let's say if it is 10% infill, then that's what you have inside. 30% is more dense. 70% is even denser. 100% theoretically, I said theoretically, that it is fully solid. So that is the difference between infill. And we have to take this into account when we are doing analysis. So over here, we have a different infill from 5% infill density to 100% infill density for the same infill pattern. Okay, so you can see that. So actually, when we have 3D printing, inside it is actually not solid. Even a thin plate inside it is not solid. And this is also various possibility of patterns, infill patterns, with the same infill percentage. Okay, so what we have here is an article from Caminero. So over here, what we have is the different in tensile behavior when we print it in a different approach, whether we print transverse vertically, or we print longitudinally flat, or we print longitudinally, they call it on edge, okay? So over here, if you look at these three, we have 1, 2, 3. Stress strain diagram, they are not the same. That depends on the way the printing direction was conducted. So over here, it's not more than 40 megapascal. Over here, when we have on edge printing, then it comes to 70 megapascal, almost twice. That means we have to be careful with this situation. And in fact, we did also our own testing using ASTM D638, and then again we are able to see that actually, yes, it is not the same. It's not the same. So meaning now that for different printing direction, we have different value of ultimate strength, for example. And it is not the same to the ones reported in the article. So over here, for example, we have 48.5 megapascal for this cross direction, and for transverse vertical direction, it is 29.8 megapascal. So that's quite big difference. Okay, so now let's go to what we have been doing in terms of FE simulation. So based on that, then when we build FE simulation, then of course we are going to make use mechanical properties based on the way we print the component. So over here is basically what we did 2 years ago. We want to check whether we do simulation is going to be is going to be validated by the testing. So we have a very simple test here, hollow box, which is simulating the wing box, and the displacement measurement is very accurate, meaning that simulation of displacement is basically the same with the test, but the stress is having 20 to 30% difference. That means we need to investigate what's the reason why we have so big gap, 20-30% of stress at certain point here, which we measure using strain gauge. Another analysis that we have been doing is curve plate with hole. The reason is, of course, because we have similar component like this in our airplanes. So meaning we need to understand the behavior of this, the stress concentration factor, for example. And also we do simulation on certain project that we do. We have a wingspan 2.6 meter airplane, aspect ratio of 9. A straight wing is something like that, straight. And then we build the finite element model, and then we have the boundary condition, and then we can easily build the finite element model analysis, and we have the deformation and the formative stress, and the result is quite okay, meaning that theoretically the result is acceptable, meaning validated. But we haven't done the test yet for this part. We do also investigations on wing joints and assembly. The reason is, as I forgot to mention, that our printer can only produce specimen or assembly or component up to 30 centimeter long. So meaning now, if this airplane, the length of the wing is 2.6 meter, meaning that we need to print the sub-assemblies, sub-components, and then we are going to do assembly. What we have been doing so far is by bonding, but we need now to know if we can do assembly by joints. So in this case here, we look at lock joints. These are the locks. And what about also doubler? So that's what we are looking at. We do a lot of finite element analysis on that. And also, I think we can see over here on the top right, when we print the wing box with lock joints. So it's tiny, but yeah, that's the lock joints. Okay, so now we are at the end of our chapter. Based on what we have been what I've been sharing just now, then it is clear, I hope, that we cannot look at this printed component as isotropic. No way, because it is not. The stiffness, modulus of elasticity, probably almost isotropic, but it is not purely isotropic. But from strength point of view, it is not. So meaning now that we need to be careful when we design it, analysis, based on, we need to foresee what kind of loading is going to work. So on the right here is going to be layer direction versus loading. So this is going to be not good. This is going to be good. This is going to be good. This is going to be bad. So that is tailoring the printing direction and layering to the actual loading itself. And what about infill? What about infill? So if we look at the structure here on the left, I think probably we agree that full solid is probably not truly correct. And a lot of time, even when we are talking, let's say 2 millimeter or 3 millimeter thickness of plate by 3D printing, sometimes inside it's not full solid. Sometimes inside it is actually as what you see here on the left and also on the right. So that looks rather similar to sandwich panel at the bottom here, which is using honeycomb core. So probably we need to look at this approach, meaning sandwich panel, honeycomb core modeling when we have this infill to consider. Okay, and we understand that for a lightweight plate, sandwich panel with honeycomb core is having a very high bending stiffness compared for the same mass but without a core. Okay, so that ends my presentation. Hopefully it's not that too long. I would like to thank you, the UiTM, for providing synergy and Lestari grants, and then of course our colleagues at FTCC who are always providing full support for whatever we do the work project together, and then also to our research assistants, students, ex-students, names are there, who have been working so hard to do whatever jobs involved, whatever works involved in this research. So they are the main actors actually. So with that, then I would like to thank you for this opportunity. Thank you very much.
Thank you very much, Prof. Wahyu, for the awesome presentation. Some important insight on the flight technology, particularly advancement in the processing, the wing prototype from balsa wood to carbon fibers, and then the use of 3D printing, which is for manufacturing of customized part components. And then for participant informations, FTTC is one of the RIG established back in somewhere in 2005, if I'm not mistaken, and recently has been upgraded to a Tier 4 research group. Right. If participants have any question, could you please kindly leave your question through a chat box? So we have actually a few minutes before we move to a second keynote presentation. If you have any questions, you can ask. You can leave through a chat box. Okay, there's one question from Associate Professor Dr. Amirazi. What would be the fatigue resistance of 3D printed parts?
Okay, thank you, Amir. Yeah, I think I will expect that kind of question. Honestly, we haven't in FTTC we haven't done fatigue investigation on this 3D printing. We intend to, so probably without hands-on evidence, I think it is not going to be proper for me to talk about values. But yes, there are articles on fatigue behavior of 3D printing, and to me, where to me, in the other day, we probably can say that the fatigue is low, for example, right? Is low, for example, but probably when we are working with 3D printing, probably whether it is high or low, that is the consequences that we need to accept as a designer, because we decide to choose 3D printing. Then if it is low, meaning that I know what would be, let's say, the endurance limit, let's say I know the SN diagram of it, because we can build the SN diagram of that, then I just make use of it, whether it is high or low. So probably it is not proper to me to say it is bad or it is good, because we are talking different range of material. What I can mention here is that uh, I can still say, based on what I read, without my own proof, because I haven't done it, based on the articles, the endurance limit is probably about 50%, 40% of the ultimate, So that one. Another important here, and I think this is even more important, is that the fatigue behavior depends on the way we print. Different print orientation is going to give us different fatigue behavior. So what does it mean? It means if we want to design for fatigue, we have to do first fatigue testing using our own facilities. We cannot just copy from any journal. So that's my philosophical answer, if I may say so. Thank you.
Prof. Wahyu, thank you, Prof. Wahyu, for the answering the question. Right, any other questions? It is very interesting, Prof, because I also last week we start printing with the not a filament PLA but the filament of stainless steel. So it will be interesting. We did also the different orientation, and then we also did the mechanical testing, and then to see the different orientation, how it affect the mechanical behavior when we print at the different orientation. Because when we talk about the new material, it has a mixture, composite of the in my case the stainless steel powder with the PLA. May I know from the aspect of this composite material, is it possible, or is there any software for the 3D printed part to be simulated?
All right. I think what Pak Hussain means here is, can we simulate the behavior of the structure with the inclusion of the fiber inside or particle inside?
Yeah.
Okay. Long time ago, we remember that in Malaysia, it is so common that we did research on using coconut fiber. Remember that? And also knaf fiber, and also knaf particulate. And we mixed that particulate with resin at that time. That probably about 10 years ago, when produced a lot of PhDs graduate doing that. So probably now we can do that also, but the basis is PLA. So the best is PLA. But now how are we going to doing all this kind of material science investigation, so that we can mix up the thing properly, and then we can look at the so-called a glass temperature, melting temperature, etc. And then we can do this without clogging the nozzle. But to answer that question, yeah, we can do that, no problem, because now what we do here is, in finite element model, we can have a combination of particulate, meaning we could have in macro micro scale, we can have our fiber as element and the resin as element. So for example, the fiber can be bar element, and resin can be solid element, and we can define the contact behavior between this fiber and also this plastic. Or it is also possible that instead of fiber, we can use particulate of carbon, particulate of steel, steel material like steel powder, for example. And then we can look at the modeling with steel as probably simple, small solid. And it is going to be in touch, embedded within a solid PLA. So that's probably my answer. So that is possible, and that is quite normal thing to do, to my opinion.
Thank you, Prof, for your answers. I think we shall move to the second keynote speaker. Thank you very much, Prof. Wahyu, for your presentation and a session about the FEM analysis of 3D printed structure. Okay,
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Right. So let's give Prof. Wahyu a big round of applause. So, ladies and gentlemen, we now proceed to the second keynote speaker. Our second keynote speaker is Dr. Judha Purbolaksono. Okay? He's from Department of Mechanical Engineering, Universitas Pertamina, Indonesia. His topic of presentation is the use of tetrahedron elements for modeling cracked solid cylinders. Allow me to brief a little bit biography of our second keynote speaker. Dr. Judha Purbolaksono is currently a faculty member at the Department of Mechanical Engineering, Universitas Pertamina. He received his bachelor degree from University of Gadjah Mada, Yogyakarta, Indonesia. His master and PhD degrees were respectively received from ITB and Queen Mary University of London, United Kingdom. His research interests includes failure analysis, fatigue and fracture mechanics, computational solid mechanics, structural modeling and design, and mechanical behavior of materials. He has published a number of scholarly articles in various reputable journals, has also been actively engaged in a number of scholarly and professional services as reviewer, external examiner, resource person, trainer, and consultant. He is presently sitting in the editorial advisory board for engineering failure analysis under Elsevier. Right, without further ado, I would like to welcome Dr. Judha to deliver his presentation. All right, Prof, the screen is yours now.
Okay, thank you very much, Dr. Hussain, for introducing my background. So, okay, Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon, selamat petang. Yeah. Okay, before I start presenting, I would like to convey my best regard, I think, from my rector. Yeah, I think to honorable guests, yeah, to this event, UiTM, Universitas Pertamina, webinar series. Yeah. This one is from our rector, Professor Wiratmaja. So it's in the regard also especially addressed to Professor Wahyu Kuntjoro. I think it's Professor Wahyu Kuntjoro was a classmate to our rector, yeah, in university. Was in ITB Bandung, and now is becoming the rector of Universitas Pertamina. Yeah. Also, I would like to have extra introduction. Basically, I was working in Malaysia for years. I think it's probably be 11, 12 years, I think, for two different universities. Yeah. So initially, I was working with UiTM, University Tenaga Nasional, probably from 2004 until 2010. Then I moved to Kuala Lumpur by joining University of Malaya. So I think for around also 5 or 6 years prior to moving to Brunei Darussalam, in Bandar Sri Begawan, joining University Technology Brunei, and then in 2019 I joined Universitas Pertamina in Jakarta. Okay, I would like to start my slide. Okay, so I'm going to. Okay, so also first of all, also I would like to thanks for inviting me to become one of the panelists here. So basically, today presentation would be related to the use of the finite element method. Yeah. So the title is the use of the tetrahedron element for modeling cracked solid cylinders. Yeah. So basically, tetrahedron element has been known, I think, many decades ago. Yeah? So it's already it's been established, I think, in the finite element method. So, but basically today here is I would like to share probably is the use of the element, the tetrahedron element, basically is with the different. I think it's just like updating, updating, because that one is quite recent. I think is finding. I think related to the modeling. Yeah. So basically, this the materials presented here were extracted from 3 different papers actually. So the first is basically recently published in the Engineering Fracture Mechanics, and then 2 other papers are now probably will appear in the next few months, I think, to publish. Yeah. Okay, so I would like to move to the next slide. So basically, it's in the outline of my presentation. So basically, is the first one is talk about the background, yeah, or introduction, because here is important. I am hoping here in the a lot participant from undergraduate student or graduate student, and then probably from this presentation, the student can further explore probably is relevant topic. Yeah? Because here is actually is new modeling, because usually is people were using special element, yeah, to model like I think is the crack, yeah, and usually is there are type we call like a wedge element, or probably with discontinuous element, probably just shifting the midpoint to the quarter point, for example. Yeah. So, and also on the other background. And then the second one is the modeling. Probably is just simple, I think, modeling strategy can be presented here. And then the result, or some example, just selected result, I think, from the 3 papers. And then in the end, it's going to be in the concluding remark. So basically, I am hoping probably the participant here, I think especially from the student, can further explore. Yeah. So probably because the application is still open. Yeah. Still open. Probably it can be used to analyze or evaluate, I think, various problem, especially in the engineering problem. Okay, here is in the right hand side is basically is the actually actually is the modeling in the crack around the crack region. Yeah? So basically, we have the crack front here. So we have a crack front here, and then here is the meshing, I think, on the corner point, and then we know here is largest contour radius. Here is important parameter, and then here is we look like here is fracture affected zone, and then here was simulated using the ANSYS workbench. Yeah. So as nearest I think is shifting, and then I think is evolving development, especially in the advancement on computational development. Right. So here is we have known that I think there are is quite famous numerical technique. The first one is called, I think, the white one, the wider application. I think here is by finite element method, and then the second one is boundary element method. Finite element method and boundary element method are suitable method for, I think, evaluating solid model or solid problem. Then the third one is finite difference or finite volume. Yes, known of the background of the computational fluid dynamic. Yeah, that one. So of course here is more suitable for evaluating or analyzing fluid problem in fluid. Or now is there is like say hybrid. Yeah, so hybrid then is a CFD and finite volume and a finite element to analyze this fluid structure interaction. Yeah. So here is, I think, is the broad range of application from these three methods. And then is we would focus on fracture mechanic. Fracture mechanic. Then of course we have known in the presence of cracks, so going to be increasing the time or the effort, I think, expended for maintenance or repair. Yeah. So here is, of course, it's going to be problem, especially if the component is part of, for example, like in the power plant, or probably in the oil and gas, yeah, or in the aircraft structure. So here is going to be very critical. So that's why is a procedure must be defined to quantify and to predict the crack component. So under surface condition. So basically is here is I think is the technique on the method has been, I think, developed, I think, many years ago. Then of course is with regard to the computer technology development right now, and then of course it's gonna be very helpful, yeah, for engineers or for analysts to analyze the problem. Then is to analyze crack component or crack problem. So the prime characterization and prediction parameter in linear elastic fracture mechanics is the stress intensity factor. I think this is most widely used in analyzing crack problem. Okay, so today our presentation will focus on the what we call is crack solid cylinder. So basically, we know that round bar or shaft are widely used in various application. So in the engineering component. Then of course is when we are facing a problem, a crack problem, then we should be carefully analyzing the problem in detail. Yeah. So basically, is the crack or like flaw or defect usually is initiated in component, usually due to the material defect, or probably during the handling, probably during the probably sending the material, then is the probably locating the component, probably in the store warehouse and so on, and also improper manufacturing processes. Yeah. So basically, here is going to be need like proper, I think, investigation. Yeah. Then with the help of the numerical analysis, yeah, so we can probably analyze crack problem or cracks component, yeah, in proper way. Yeah. So basically, is in literature is many failure analysis has been reported. Yeah. So basically, is actually is usually is the most famous I think is journal is the engineering failure analysis. So in the journal is I think is published a lot of I think is paper associated with the crack problem. Okay, the need of the stress intensity factor. So basically is to quantify. So to quantify the usually the residual strength of the component, the crack component. And it is also particularly stated in the practice codes, such as the British standard, especially in the BS 7910. Usually is for assessing the acceptability of the defect of flaws. Then also in the power plant and the oil and gas. So usually is they are using the data of the stress intensity factor, usually for the purpose of maintenance or schedule inspection. Then here is stated in the API 579. So here is usually is specifically coded for fitness for space, and also in the power plant, usually in ASME, FFS DS1. Right, so we move to with the help of the computer development, so the one in the computer graphics. So I think is we can feature I think is the crack, yeah, especially in the crack region in more detail. Yeah. So basically here is going to be very helpful to us, especially for as the analyst or as the engineer or probably as the designer, for example. And then is with the help of the computer graphics. So also the interactivity of the computer graphic with is going to be very useful or helpful, I think, to us, I think, in analyzing crack problem. So nowadays there are many finite element software package, yeah, available in the market. Yeah. So such as ANSYS and Abacus, Hypermesh, MSC Nastran, COMSOL, etc. So actually there are many options. Yeah. So it's available in the market. So so in here in particular is about the result for stress intensity factor are reported in literature. Mostly is the solution usually for larger ratio of the crack depth of the cylinder diameter. So as only very few, I think, is probably paper presenting result for small, relatively small ratio of crack depth of cylinder diameter. So, and other than that is in finite element modeling, in dealing with the crack problem, until today, we still have problem called as the corner point similarity. So basically in the corner point similarity, then I will show later. So basically here is the sum of the stress due to the stress intensity factor and the corner point similarity itself. Okay, so here is the most stress intensity factor solution reported in literature for larger radius. Yeah, so that was already mentioned earlier. So with the nowadays advancement, so in the computational development, so of course here is going to be make it possible for developing a model for small crack surface, small surface crack. So here is going to be also the interest, yeah, because it's if we are doing damage tolerant analysis, for example, so basically is we will have many scenarios. Yeah, usually we need to initially introduce relatively small crack. Yeah, usually if in the aircraft structure, usually in the, for example, the wing section usually is we have usually guidance for example from GAA, the one is European aviation body, or FAA, that one is from aviation from US. Usually they mention stated like the Probi is to have like initial crack, for example, usually is in the one is a path-through crack, yeah? Can be like surface crack or corner crack, and then usually is relatively small, usually is 0.005 inch, it's relatively small. Then from then is we need to probably is apply probably is the fatigue loading, and then so that's why is we need like stress intensity factor solution, I think, for small crack. Then it's gonna be very practical if we can like say like fatigue crack growth analysis, probably is not using like finite element or boundary element method, but probably is just using the formula. For example, we can adopt, for example, NASGRO equation, for example. Then from here is we can be doing like fatigue crack growth analysis. For example, is cycle by cycle, and then is from there is going to be from there is we can probably have a result much quicker, yeah, rather than is using the finite element or boundary element method. So basically is in the literature, basically is crack on the round bar in here. So basically is particularly he has been reported in number of paper, and then it's in the shape of the probably crack surface crack is just nearly of semi-elliptical shape. So here is, even if we are doing experimentation, after we introduce probably like initial crack, then the crack is tend to have a shape in semi-elliptical shape. Okay, here is the example. Here is from I think is from literature. I think reported in the Journal of Engineering Failure Analysis. So basically is the upper one. So basically here is in the smooth cylinder, and the lower one is basically in the here in the called like the solder fillet. So it's usually considered like step solid cylinder or solid bar. So basically is the crack is going to be initiated and the solder fillet here. So this here is of interest in practical application. Then the data of the solution is needed, and only a few, I think, is paper, I think, reported in the result is typed in the step bar here. Yeah. but in the smooth cinder is quite number. But of course, in terms of modeling, is we need to further explore. Probably is more practical way in modeling crack region. Okay, here is we can see here. So basically, is just to briefly explaining the phenomena. I think in the crack tip on the crack front. So basically, is for example, here is the crack body, and then is here is the crack surfaces. Then is for example, we take like the reference point of here as the crack tip. Then for example, is subjected to bending loading or torsional loading or tensile loading, and then of course the nominal stress I think is here is going to the infinite. Then of course the material is the material has a limitation. For example, is material has the yielding strength. Then beyond this point, of course, is the material will experience yielding. Then it's going to be like in the elastoplastic or fully plastic condition. So that's why is seen the stress is going to be infinite. Then it's going to be how to analyze probably the state of stress around the crack tip or in the around the crack front. So here it's called like a stress intensity factor. Here is for describing the stress state. Stress state, I think, in the crack tip or in the crack front here. Then I think is most common technique, I think, to calculate or compute the stress intensity factor is the first one is G integral technique. Probably here is I think is invented or probably is proposed in around in 1960s, something like that. Then also the crack opening displacement. So these two technique is very well known or famous method used to calculate the stress intensity factor at the crack front or in the crack tip. So the lower one here is I think the what we call is J integral. So in this work actually is using a J integral. So basically here in the one, if we take the reference point here as here is the crack tip, then we have I think is number of U contour. So basically as here we utilize the data from displacement and also the strain. Then is put it in the formulation. Then we will obtain probably actually here is the idea is coming from the strain energy release rate, and then is converted into the stress intensity factor. Okay, here is an example. So it's basically is down here is actually is the loading mode. So we have known the one is we have three modes. So basically in the mode 1, mode 2, and mode 3. So the first one is in the opening mode. The second one is sliding mode or in plane shear, and then third mode or mode 3 is out of plane shear. So basically, if we have this in the say like call inclination angle, for example, then it's subjected to the tensile load or the tension. Then of course will result in three loading modes. So of course we have the opening, the sliding, and also the out of plane. Yeah. So basically, of course, if the one is if the alpha equal to 0, so subject to the tension, we do not have the loading mode for mode 2 and mode 3. And if we subject to say if the alpha equal to 0, then subjected to the torsional loading, then we do not have result for mode 1. Actually, we have, but it's close to 0. Yeah. Anyway, so I think in the practical application, I think is the opening mode on the mode 1 stress intensity factor is actually is mostly used, I think, in the practical application. So basically, so that's why is on the mode 1 is more likely, yeah, more likely to happen. So and then that's why in in many I think analysis usually is people focus on the use the data from the mode 1, yeah, mode 1. But now it's a lot of the I think is research I think going on. Yeah, actually it's now they also considering the mixed mode, yeah, mixed mode. Actually in terms of the just pure calculating the SIF, or probably is doing the fatigue rate. Right, so here is the formula just for brief. So basically here is for in infinite body. So basically if we have stress intensity factor, so usually is defined as the loading. So that one is can be like shear stress, or maybe like tensile stress or nominal stress. So basically is we have this. So then it's actually is here is for infinite body. If we have like a finite body, for example like this, that one is considered as finite body. We have finite, that one is in the cylinder. So of course we have called here is beta here is called like the geometric factor. And then usually it's the data I think needed for I think practical application usually is normalized. Stress intensity factor is called beta here. So basically here is K over the K0 or KO. Yeah. So basically as to make it easier, usually as we prefer to use A equal to 1, so it's going to be U90. So it's easy to convert into the actual value. For example, if we have different magnitude of the loading, and then we just simply I think converting, and then just one for example is the as long as we know the loading, then we can find the stress intensity factor. So usually is some data is available in the handbook, and then also in the practice course like the API or BS or ASME code. Yeah. And I think it's here is we can use the one numerical modeling by using finite element or boundary element method. So what we are doing, so what we have done actually was using ANSYS. So basically ANSYS workbench. Yeah. So that one is ANSYS 2019 version. So then we call 2019 we we remember COVID-19. So it's so that one also is not good thing. Yeah. And the other one is actually is we were using BC software. So basically here is dual boundary element method based software package. So here is developed in Southampton, United Kingdom. Yeah. And we have to say thank to University of Malaysia because they have the software. And so of course here for the benchmarking purposes. Okay, here is just we know that one the tetrahedron, yeah, tetrahedron element. So basically is we have 10 node element. So here's quadratic element. So in the left hand side, and the right hand side is the we call hexahedron element. Here basically is we have 20 node. Yeah. So basically is if we have if each node has 3 degree of freedom, so it's gonna be we have degree of freedom to be 30, and then here's also time 3 is gonna be 60. And the lower part here, so basically here is the strategy, I think is the modeling strategy by the dual boundary element method. So basically they use a different method for example is they have discontinuous element, then we have as a discontinuous element, then we have also continuous element. But all here we what we use here I was using I think is all continuous element. So the purpose of this presentation I think to present like fully no special element was used. So basically we try to introduce like ultra fine meshing, yeah, around the crack region. So here is shown here. So basically is the meshing strategy. So in the smooth cylinder, So as I mentioned earlier, we have the largest contour radius, and then also the fracture effective zone. So usually here mid semi-ellipse. So basically we can see the difference between the hexahedron and also the tetrahedron. So after we generate meshing, then here is the appearance. I think is we see the one is the corner point. Yeah. So it's around the corner point, something like that. Actually, the one is here is along the crack front over here. But here is the section view. So something like this. This one for tetrahedron, and here for hexahedron. Yeah. So based on the empirical exercise. So we propose or suggest or to recommend to the user to use probability is around 0.25 until 0.5 A. A is here is basically is in the crack depth of here. Yes, here is so far is so good. Yeah, when we choose either one here, but of course is we can also make the smaller than this one or larger than this one. So if we have would like to have a rough calculation, for example, then of course we need to use a larger size. For example, equal to A or probably 0.75. And of course, the one is the runtime can be shorter. Yeah. Okay, that one is the step cylinder, so it's look like this. So of course, when we have here is more likely crack will be developed, I think, in the solder right here. Of course, here in the area or region of having the largest von Mises stress or nominal stress. So it's the crack is going to be introduced here. So of course, before we introducing crack, so we have to do like a stress analysis first. Then is to identify the location or the most likely location of having crack. So basically, then from here we can select based on the probability node, yeah, in mesh. And then usually we can use this like Prof here as usually the software like in ANSYS will showing the one is the maximum location. Then probably we just take that location for introducing a crack. So it's quite similar. The difference between the smooth and the step cylinder is just we need to like doing like stress analysis. Okay, here is the benchmarking. I think it's done. Then it's actually is compared to published result and also compared to the result by dual boundary element. So it's a very good agreement shown here. So basically, as we have noticed here, basically there are some improvement in some extent here. Yeah. In comparison to the published result, because the one is probably published in the 2006, and then is in 1986 and also 2004. And then, of course, it's with the current development in the computer technology and also in the computational development. So, of course, it will result in the better accuracy. So of course, is here is the important. Then here I think is I think the comment last time I think is by the editor is editor. So the one actually is this one is something new. The one is updating. Actually the element tetrahedron element is already known many years ago, but by without using special element, just the one just try to have like ultra fine meshing around the crack region or in the crack front, then it looks like the result is very good agreement with those by dual boundary element method. So basically, since dual boundary element is known to be like semi-analytical, they can treat, I think, as a singular problem more conveniently. So that's why is we need to do benchmarking to dual boundary element method. But for practical application, of course, engineers would like to use finite element because the availability of the software in the market, and also the one is also the running time, I think it can be much shorter than those by using dual boundary element. So people tend to prefer using a finite element method rather than dual boundary element method, because it's also in terms of the formulation, the matrix is very dense. Yeah? So resulted from dual boundary element. So basically, is my PhD thesis actually I think was using the dual. I think developing code, yeah, by dual boundary element method. Actually, that one is for large deformation. So in the rational plate, and the moment the project was under, I think, like sponsorship, but actually that one is related for the project. No, and the moment is actually the project is for Airbus 400. Yeah, formulated military version. So that one is the aircraft was having, I think, a maiden flight, I think, in 2009. But that one is for flat plate. Yeah. But after that, actually, is many development with the shell shape and also with the multi-connecting body as well. Okay, here is the trend. So we can see here is the between the result, I think, between the Tetrahedron and hexahedron. So as the result is quite identical, only the problem here is we are using the hexahedron. The problem is cannot, I think, have a good result, I think, in the corner point over here. Yeah. And also if we have, say, in the mode 3, so we can see here is the solid line here, I think, is by of using the hexahedron. So actually, it's comparison the dual with the result by dual manual is a bit shifted away. And but if we are using tetrahedron, I think it's quite good in good agreement. But of course, in the corner point, we still have problem, I think, in the mode 3. But for mode 1 and mode 2 are sound to be in good agreement. Here is for normalized research. So basically, is alternate from the smooth cylinder for different crack aspect ratio. For example, we can see here why A over C is the one is saying the A over C is smaller. So the pattern is going to be something like that, like in the convex shape, and then if the one is larger. For example, A over C equal to 2, then it's going to be in the, say, like concave shape like this. But A over C is equal to 1, so that one is still make like in the concave shape, but here is due to the corner point similarity over here. So here is due to effect of the corner point similarity. So that's why when A equal to C, so it's according to this. So of course in the here you will see that one is in the corner point where has a larger magnitude. Then here with the further with the current development in the computer graphic, so we can view the actually here the stress contour. Yeah. So basically here hardly reported in literature. Yeah, hardly reported in literature. So basically is we can see here. So the one is if we back here. So why here is the shape is like this, and then for the larger C, the shape is going to be like this. Yeah. So the one is we can view in more detail, and then actually in the stress distribution around the crack front, then so we can see the different. Then actually we can imagine like we have a plate with small hole, and then it's in comparison with the plate of having the larger hole. So basically the one also represent that. Yeah. So basically is the one the SIS tend to have the so the one is going to be in the red color is going to be here. So if we see back here, so here so this one is red color is going to be maximum in the deepest point. So then in the corner point is going to be like yellow here. So in comparison for larger A over C, so of course here is going to be a red, so around the corner point. So as we can see over here, so of course here is showing like this. Yeah. So in the A over C equal to 1, so that one is the red color, the contour gonna be almost evenly distributed. So we can see over here is the one slightly, but here is slightly larger, but not slightly, it's obviously larger. But if we see the one is the effect, for example, later in the step bar, so we can have different one. Right. So here is for result for in the step cylinder. So it's similar. So we can see in the one there is some like transition, I think. So it's from the concave to concave shape. So if we have something here, actually we can hear also feel, I think, in the stress diffusion around the crack region. So they want similar the explanation, but we can see the different, like here is look like a little bit flat like this, yeah. So, but of course, here is for smaller aspect ratio, crack aspect ratio. So actually, is we have, I think, here is the result is shifting. So it means the stress, the corner point similarity, we still have a problem for smaller size or for smaller crack aspect ratio. But for larger, as I think is going to be, I think, having a better agreement. But of course, in the corner problem, we still having the corner point similarity. Okay, we can see over here is quite similar like this. So here is the result from, I think, is step bar. So I think as we can further explore, for example, in the piping system, for example, probably in the pressure vessel. Then, so I think still we can still further explore, I think, the application on the use of the tetrahedron, or probably is the also the hexahedron element without using the special element. But here is the normal stress, so I think it's similar like the previous one, only different the crack aspect ratio. Here basically it has been published recently in the engineering fracture mechanics, so that one just to share. And then here is for the mode 2, I think, the one for the incline crack, so subjected to the tension load. And then we see here is in a good agreement between final element and dual boundary element result. Okay, that one is in the mode 3, we still having problem. So basically is we can notice here. So here is especially in the corner point. So we have, I think, is some deviation here. So that's why we have to probably later for future work, probably need to use higher order tetrahedron element, I think, of using probably 20 or 32 node, for example. And then probably we can probably treat the corner point problem probably is probably accurately or conveniently. Okay, here is the concluding remark. So basically, we can see over here. So basically, for small crack, yeah. So and also for larger A over C, then for mode 1, and also for mode 2 is for A over C less or equal than 1. So basically, is the result by FEA was found to be in good agreement with those by dual boundary element method. Then we have shown, I think, before that mode 3 or tearing mode or out of plane, I think is we need like further treatment, I think, because is here is still have a problem with the corner point similarity. And then basically is the SIF, I think, or especially for mode 1 and mode 3, away from the corner point, where generally the result by FEA and dual boundary element was found to be in good agreement. And then we can also notice for example, effect of the crack aspect ratio, crack size of diameter, and also loading mode here will influence the SIF. And then as for step bar, so step bar over here, so basically the severity out on the corner point, I think here is intensifying the effect of the solder fillet here, causing or resulting in probably stress concentration. So especially when D over D in the one is large or R over D is small. Yeah. So here we have probably is severity of the corner point singularidity. So solder fillet. So basically we can see from the I think graph basically had a stronger effect actually on the corner point rather than in the SIF around the deepest point. And the last one is basically we can also notice I think previously basically the influence of the solder fillet on the stress intensity factor around the deepest point is getting lesser when the ratio of the A over D or the ratio of the crack depth over the diameter of cylinder is increasing. Okay, and this one of my, I think I take a lot. Many thanks that one for your attention, or probably I take a more time here. Okay, I pass back, I think the time to Dr. Hussain.
Thank you very much, Prof. Judha, for your very informative presentation. Now we move to the question and answer. Probably we can have a few minutes for the question and answer. There's one question from the participant. I believe this question is to Dr. Judha from Dr. Nur Hisham Muhammad Rani. His question is, how confident you are in the predicted result obtained from the finite element models, since the model are developed based on assumptions, these are material properties and boundary condition. The accuracy of the finite element result is a function of element types, material properties and boundary condition used in the finite element model. How do you address this issue?
Right. So thank you. The question from Dr. Hisham. So basically, how confident? So basically, is so that's why when we start of having the modeling by using finite elements. So of course we need to benchmarking. So this is actually for the isotropic. So basically is the properties is quite uniform. So probably for further, for example, like different type of materials. So of course is we have further consideration, especially for example, like we are doing, for example, say crack from say crack it a composite component, for example, then of course we have to be more careful. Yeah. So for this is so for boundary condition, I think is we see here we have tried to make the boundary condition as close as possible to the say its real condition. For example, is say like the percentage here is the boundary condition is quite simple. So basically, say like the inclined crack, for example, if I saw here, for example, here is for example here for inclined crack, for example. So of course here is the one is pretty simple, I think, configuration. So of course is the important thing here is now is we have what we call is there is features, I think, in the software, I think in the ANSYS software, and I think is here is we know is we can play around with the size of the LCR here, the largest contour radius. So how confident then is from here? So from here is basically is we have a good, for example, like a meshing over here. For example, like we are using the tetrahedron, for example. And then of course if we need say comparison, then so if the result is probably is say is in good agreement with those by dual boundary element method, because actually is dual boundary element method is more suitable technique to evaluate crack problem. Until today, like Airbus or Boeing are still using dual boundary element, but they ask just to generate the say like simple say like simple model. They cannot say simulate with the full scale model. The only way is we have to do say for example, if you have like say is a closer model then to the real one, then of course we need to use a finite element method. Yeah. So basically is we can see over here. So the result is we have, I think, is done by FEA and done by dual boundary element method. So how confident is now is quite confident, because now is we try to use ultra fine meshing. Here is we can see over here. So if I think over here. So here is very fine meshing, or we call like ultra fine meshing. So of course is we are quite confident, but we still have problem on the corner point until today. Yeah. Until today, we have still have a problem. I think here still need further development in dealing with, I think, how to estimate the stress intensity factor and the crack tip here. But away from the current point, I think is already confident enough. Yeah? And the result is quite, I think, is promising. Yeah, if we see from here is quite promising, but still we have problem in the corner point over here. Yeah, corner point. So of course, with the boundary condition, I think as long as we have to try to I think apply the boundary condition as close as to the real one. So for example, if we have complex problem, for example is the structure made of the few component or connecting bodies, for example, then of course we have to be careful in applying boundary condition. And of course is there's a lot still a room for development, or a room for I mean opportunity, I think, to explore, I think, other relevant topic, yeah, probably for other application. Yeah? But for coding, for example, of course we need to suggest, of course we need to hire, we used to higher order of element, because here is just use 10 node element, but it was already quadratic. And then in say in a hexahedron element is we use 20, but seem to be like the result I think is I think done by using hexahedron is look like better than using the hexahedron element. Yeah. So as in terms of confidence, is quite confident. Yeah, in terms of the as long as the boundary condition is correct, then as long as we know the material properties, the one is of course is we use, for example, like orthotropic as was presented by Prof. Wahyu Kuntjoro, and then we have to be careful in defining the contact also layer by layer, and then of course here is need to be taken in consideration. Yeah, probably is probably that one is my response. Probably is Dr. Hussain probably tadi probably would like to have further question. As long as that one is result, but actually for fatigue crack growth, yeah, for fatigue crack growth is basically is we can utilize, I think, result in the say is the I think is away from the corner point, and then is we can actually use like extrapolation. Yeah, some other researcher here, I think, like Carpinteri and 1C, Yeah, that one also new one. Yeah, I think they are using extrapolation, yeah, to have, I think, as to approximate the SI path at the corner point. Yeah, that one is the issue, I think, of using the finite element. We still have problem at the corner point. Yeah. Probably it's also good to explore of using a higher order element. Okay, that's my response, Dr.
Okay.
Hussain.
Right. Thank you very much for Dr. Judha for the detailed explanation on the question by Dr. Nisham. Hope that Dr. Nisham is satisfied with the answers by Dr. Judha. Is there any other question from the participants?
Yeah, basically there are a lot of room, I think, for exploring. I think is of using this element. I think probably is also good for final year project, and also probably is master project. I think still there are a lot of application. So
I think that's a very good opportunity for the future collaboration when we have a co-supervisions between UiTM and Pertamina. We'll be focusing on the aspect. Right. Any other question from the participants? So no more interview. Actually, I have whether I want to know whether Prof from Wahyu is still here or not, because I'm missing one question from
Yeah, I'm
the participant.
here. I'm here.
Okay. Is it okay?
Sure. I'm
All
still here.
right. Okay, there's actually one question from Mr. Shazwan Johari.
Okay.
From UiTM Pasir Gudang. Assalamualaikum everyone. I do have one question. PLA is known for being soft or deformed under high temperature, probably above 60 degrees Celsius. Is there any way to overcome this from happening, or is this problem unavoidable?
Okay, that is a very pertinent question, because that indeed is the problem, as also probably Dr. Hussain very much aware. Yeah, the problem with PLA is that it is popular, but now the challenge is what happen now if, let's say, it is being exposed to operation with higher temperature. In fact, PLA is not recommended for operation which is beyond or higher than 45 degrees centigrade. So some people say 50, 55, I would say probably 45 degrees centigrade, because as everybody who are familiar with doing 3D printing with PLA, if they print with PLA, put it on the window, it will change the shape.
Yeah.
And now we can imagine if you want to build an airframe using PLA, which is going to fly in the sky, and then under hot sun of Malaysia, then that's a problem. So what we do here is actually, I'm not talking from chemical point of view, chemistry. Chemistry is going to be for Dr. Hussain to answer how we can make it better. So we just do coating, basically. We do coating at the surface of this PLA airplane, and then by doing that, yes, we can I'm not saying make it better, but we can protect the airframe better. So what you need to do is just do coating. There are possibility by painting or by having resin, for example. So yeah, we can do it in that way. But I'm not going to mention how chemically we can make it better. That's a material science guy to do. Is that the question, Dr. Hussain?
Yeah, I think so. Actually, the one that by the team by FPPC doing coating as a barrier to avoid the direct contact or from the environment to the PLA directly. So another approach probably on the development of the new material which can sustain, or which can you can operate at the higher temperatures.
Yes.
So
Or
yeah.
alternatively, probably we can use ABS
Yeah.
plastic, but of course our printer is not doing that.
Okay.
So in the end of the day, we are working with what we have. So that's the reality of it. That's the reality of it. So
Yeah.
thank you. That's my answer.
Right. There's a room for opportunity for the future research to venture. Right.
Yes, very true. Correct.
I think there's no more question from the panel, from the participant. I would like to take this great opportunity to thanks to both presenters for today's session, our first event webinar between UiTM and Universitas Pertamina. For the announcement, I would like to inform to all participants that tomorrow we also have another webinar today, which will be led by UiTM Penang, which will be moderated by Associate Professor IR Dr. Salina Budin, and the speakers from UiTM is Prof. Madya Dr. Kwe Mehi, and from Jayabaya Universitas Pertamina is Dr. M. Purwo Kadarno. Okay, so please feel free to attend tomorrow's second webinar session. The topics of Dr. Purwo is finite element simulation of punching of high strength steel sheets, and Prof. Dr. Koi on strong ties between solid mechanics materials and manufacturing. Right. Hopefully, thanks again to Prof. Wahyu and Dr. Judha for the informative and interesting talk to the audience, and also to the audience for the active participation. Hopefully, the presentation will be beneficial for everybody. And lastly, for participants, kindly fill up the Google form provided for the attendance and to claim the e-certificate. And I think before we end our webinars today, let us have a group photo. Maybe Puan Cik Hidayah can print every group photo. Participant can switch on your cameras. Or the layout.
Okay.
Okay.
Ready, yeah?
All right.
1, 3. One more time. 3. Okay.
Right, thank you very much, Puan Cik Hidayah, for your cooperation. And I would like to thanks to Dr. Koi and the team from Penang for this opportunity. And as a co-organizing committee, I also would like to thanks Prof. Wahyu and also Dr. Judha for the today's session. And we look forward for the future collaboration, inshallah, in the field of solid mechanics or anything that we can collaborate, inshallah. Thanks again to all participants for your kind participation. Look forward to meet all of you tomorrow at 10 o'clock Malaysia time. All right. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi.
Okay. Thank you, Dr. Koi. Dr. Saina.
Thank you. Good job, everybody. Thank you.